History of late glacial runoff along the southwest margin of the Laurentide ice sheet. Alan Kehew and James T. Teller. This is now back in 1995. I'm guessing I probably read my first paper by Teller, certainly in the 80s. I'd have to go back and look, maybe mid to mid 80s, late 80s, perhaps right in there. He's been writing on this for a long time, studying this for a long time. One thing he says here that's interesting, he's talking about the isostatic depression. That's important to keep in mind because the ice was pressing down on the land. You have to picture what that did. Was it caused a depression in the land? So as the ice retreated and melted back, you had this tremendous ponding of water around the perimeter of the ice sheet. Does it make sense? Right? Now, as the ice sheet is diminishing in mass, the water mass is growing, right? Until you get some kind of an equilibrium between the proglacial waters accumulating and the runoff of those waters into the ocean, right? So if it's accumulating on the south side, it's going to probably feed into the Mississippi watershed, and that water is going to be routed down to the Gulf. If it's the mid-southern range of the Laurentide ice sheet, it's going to probably end up in the Mississippi. Okay, so but as that ice is retreating back, it's also shrinking. And as the water is draining off, the mass of weight, the multi-hundred billion trillion tons of weight is being reduced. So now the land starts lifting back up. So as it's lifting back up, what's going to happen? Accumulating waters will tend to drain off, right? Sometimes it could be that the rising of the post-glacial isostatic uplift is not always going to be perfectly uniform. There may be episodes in there where it's seismically abrupt. You see what I'm saying? Where the uplift might be actually a seismic event, 5, 6, 7, even earthquakes. Right? Now, what that might mean is if you have a sudden uplift, is that you're going to have a sudden draining of those ponded waters that have accumulated around the perimeter of the ice sheet. So when we begin to look at this idea of post-glacial flooding, we have to keep that in mind, that there's a variety of processes that are ultimately going to feed into the continental hydrological system. And what we're looking at here, and I think this is one of the things that has sort of, I think, it's confusing about the dominant model of ice dam failures that we're going to be really, really looking in depth at, this idea of an ice dam and the efficacy of ice, glacial ice, to serve as a dam for water to some given pressure, right? Because anytime you accumulate water behind some kind of a barrier, whatever that happens to be, the pressure is going to be related to the depth of the water, right? It's also going to be related to if water is flowing into the system. If is water flowing into a reservoir, you have a dam, creates a reservoir. Is water flowing into the reservoir? So if you have a reservoir that's dammed, obviously you have to be draining water off somewhat commensurately with the amount of water draining in from the surrounding terrain. And if you have too much rain, it exceeds, right? The danger is that you have an overtopping of the dam. That's what happened with the Teton Dam in Idaho when that failed. It actually started by piping along the side, but the water had come up nearly to the top. So the water, once it started through, it quickly eroded the dam, and away it went. St. Francis Dam, I think, in California was an example of an overtopping dam, right? Problem is with glacial ice, if you're looking at a concrete dam or even an earthen dam, obviously the dam material is much more dense than the water that it's retaining, correct? But in the case of glacial ice, the glacial ice is going to be less dense than the water that it's retaining. So that creates a problem of physics right there that I think tends to be ignored. But the question is what's the origin of the water ultimately? That's, to me, what's being overlooked here. So anyways, coming back to Lake Hind here, And I brought that up, James Teller, because James Teller is now co-authoring papers with the Comet Research Group, which I think is a very significant milestone in these studies, because now we've got a geologist who's probably one of the world's experts on glacial paleohydrology, joining forces with the Comet research team. I think this is a really cool thing. And so this paper that came out last year, January of last year, is entitled A Multi-Proxy Study, multi-proxy, not just one proxy, but multi-proxy study of changing environmental conditions in a Younger Dryas sequence in southwestern Manitoba, Canada, and evidence for an extraterrestrial event. So they get right into the paper and they say multi-proxy analysis of a sequence spanning the Younger Dryas in the glacial Lake Hind basin of Manitoba provides insight into the regional paleohydrology and paleovegetation of meltwater rivers and lakes. So paleohydrology simply means the study of flowing water long time ago, right? Paleovegetation is, okay, what kind of vegetation was growing in a given landscape or a given terrain X number of years ago. Paleovegetation, paleo meaning old. So if you have a lake basin, that lake basin is going to see if it's a collection basin, and all kinds of pollen and organic material from the surrounding vegetation is going to make its way into that lake, isn't it? So that's going to accumulate in the sediment in the bottom of the lake. So if you go in and you look at the pollen, you look at trees will leave their pollen, and you examine that, you can tell, well, wait a second, this is larch trees and spruce trees growing here, and then they were replaced by a lot of alder trees. Well, alder trees grow in a much warmer climate. What does that tell you? So this is looking at the paleovegetation and the kinds of things that grow and thrive in a given environment. It's going to tell you quite a bit of information about what was going on in that environment, right? So that's what they're saying here, is that they do this multi-proxy analysis of this Lake Hind. I'll pull up a map here in a second. The lake was dammed by the Laurentide ice sheet, and it overflowed into Lake Agassiz. Hello, Lake Agassiz. Introducing Lake Agassiz. Lake Agassiz is going to be one of the next big things to talk about for multiple reasons. It was a phenomenal lake, and of course all freshwater, but it was really like a giant inland sea, temporarily formed, ponded against this shrinking Laurentide ice sheet. Say that the pre-Younger Dryas interval records rapid sedimentation from meltwaters that headed in proglacial lakes in the Canadian prairies that are known to have been catastrophically released when ice or sediment barriers were breached. Pollen in this phase is dominated by pre-quaternary forms eroded from Paleocene bedrock. Let's stop and say that again, so we just don't go beyond this and people don't know what the implications of this are. Pollen in this phase is dominated by pre-quaternary forms eroded from Paleocene bedrock. Pre-quaternary means that it's older than 2.6 million years. So there's pollen in this layer, right? Right at the Younger Dryas, that is pre-quaternary. Now, the pre-quaternary, where did that come from? It was eroded from bedrock, which was undoubtedly millions of years older than that, right? So now you have to think, eroded from bedrock. What does that mean? Well, it means that the water that came through there and deposited this, whatever else, it was eating its way directly into bedrock, and it was exhuming the contents of that bedrock, which included these pre-quaternary pollens and things. So over 2.6 million years. Now, so it says it's dominated by those forms eroded from Paleocene bedrock at the onset of the Younger Dryas at 12.8 thousand years ago. the sudden appearance of concentrations of nanodiamonds, high-temperature magnetic spherules, platinum, and iridium provide evidence of an extraterrestrial event that others have identified at more than 40 sites in North America. Major changes in oceans and climate and the catastrophic outflow of nearby Lake Agassiz at the onset of the Younger Dryas may be related. Now, this is all really potent, important, interesting stuff. Because here's a group of scientists now going, okay, so we've got this layer of the ET proxies that correlates with 40 other sites by now documented by at least eight different independent teams. And it correlates in time precisely with this event that's been dated now, the catastrophic outflow of Lake Agassiz. So what caused the catastrophic outflow of Lake Agassiz? Or how long had Lake Agassiz been there? I think what this might be saying, essentially, is they're saying Lake Agassiz, okay, but how long was Lake Agassiz accumulating, and why did it suddenly catastrophic outflow at 12,900 years? See? And this dates precisely with the proxies, the nanodiamonds and the microspherules. So they're saying here the catastrophic outflow of nearby Lake Agassiz at the onset of the Younger Dryas may be related to the deposition of these concentrations of nanodiamonds, high-temperature magnetic spherules, platinum, and iridium. Now, that's a huge step to say that. They may be related. Yes, Brad will testify. We were saying that 20 years ago. They're related. Not that we knew about the impact proxies. I didn't know about those 20 years ago. I don't think Brad did. I don't think really anybody did 20 years ago, knew that there were these layers of nanodiamonds precisely at that Younger Dryas boundary. However, 20 years ago, we were surmising that the flooding and the catastrophic outflows were triggered by cosmic impacts. I mean, we were thinking that and talking that and discussing that in 1998 when we made that first 2-week excursion over the Scablands. Yeah, 1998. And that 1998 trip was the culmination of really almost like 10 years of thinking and reading and research and map study and all of that from multiple different fields, not only the paleohydrology and the creation of the channel Scablands, but what was also available about impact geology up to that point. Because you know that from the early 1980s on, there was a renaissance in the studies of impact-related sciences. Okay, so now we have this catastrophic outflow of glacial Lake Agassiz. So what we have to do, in a sense, is go, okay, glacial Lake Agassiz. What do we know about Lake Agassiz? You know, how big was it? How much water was there? This catastrophic outflow. What was the discharges? How much water? And where was the catastrophic outflow? All right, right here. See that little blue shape? It's at the southwestern corner of Manitoba. That represents the position of glacial Lake Hind. Now, Agassiz, if you look at Lake Winnipeg and Winnipegosh and Lake Manitoba, these lakes up here, they're all occupying basins that were part of Lake Agassiz. And right down here where this bump is on Minnesota, see that bump? That bump is right there is the location of the Big Stone Lake and is the temporary southern outlet of Lake Agassiz. So that's right down there. Now, we're going to be looking at this study that was in this lake right here, which at this time now is the most northern impact proxy site that's been studied at this point. So at the Younger Dryas, then the assumption is that the ice had just receded just north of where Lake Hind is at that time, at the onset of the Younger Dryas. You can see right here, right on the border, there's North Dakota and Lake Agassiz, and there's your Lake Hind, right? It's just separated a little bit. It's almost a part of Lake Agassiz, but not quite. And then you can see where Lake Agassiz comes down in this tongue right here. And you see where the tongue stops right at the bump on the western border of Minnesota. Right there at the end of that bump, that's where Big Stone Lake is. And for a while, that was the temporary outlet, the temporary outburst point for Lake Agassiz. But it actually had multiple. It turns out now there's evidence that it also catastrophically drained along the margin of the Laurentide ice sheet to the north, right? So the box right here, the purple box, encloses the area that we're looking at right here. See that? So there's some interesting stuff going on here, some very interesting stuff. We're going to be looking at Lake Hind, which is right in here. Then you've got this Turtle Mountain, the upland that's right here, this kind of teardrop-shaped upland. We'll be coming back and taking a closer look at that in our examinations here. So let us continue on. Here is an example of some of the things that they found at Lake Hind that will now be recognizable, I think, to most people. Here's some of your magnetic spherules that they started uncovering. Look at this one. This one actually, because these were produced in high temperature events, and there was also collisional. These in the high energy plume that these spherules formed in. These spherules are flying around colliding with each other. See, and that's what you're seeing right here. That's what you're seeing right here. These broken out parts where the spherules collided. In some cases, smaller material in the heat of it was welded to the spherules. So what they're finding there is like what's being found at dozens of other Younger Dryas boundary sites and this is what we've been talking about. So this should be becoming pretty obvious to people at this point. And then we did look at this last week. This was the spikes of nanodiamonds, platinum, iridium, sediment grain sizes. All of this was the analytical studies. There was a couple of interesting points. One was this prolonged deposition of platinum, which actually went on for about 2 decades. So it's like the planet is getting this 2-decade-long dusting of platinum. That's pretty bizarre. So Lake Hind, let's look at some maps here. I've put some maps together. This is from this is actually referenced in the paper we were just reading from, but this goes back to 2002. And this is just a simple map of the area of where Lake Hind was. And it's showing there's an Oak Lake, which is there now, is the last remnant of Glacial Lake Hind. And a couple of things I want to show you, call your attention to, is the Souris River right down here running kind of diagonally across the screen. You've got your Trans-Canada Highway up here. You've got the Assiniboine River up here. And then these gray areas represent deposits of sand. Now, up at the top, you've got this direction rose, as it's called. And what it's showing is by looking at the grain orientation of these sand deposits, they'll find that there's a dominant direction that will be a paleodirectional indicator. In other words, look at the array of this gray material here, and you'll see it's generally very parallel to this long arrow on the directional rows. You see that? That's because this is a water moving this way across the land, depositing this stuff right here. You see that? And then you have this large deposit of sand down here that flanks the Souris River. Okay, so this is kind of the layout of it. We'll go over here to the screen on the left, and the Assiniboine River is flowing in this channel. Can you see this channel right here that kind of loops down, comes across, and loops back up? See Oak Lake over here? Okay, this is our lake right here on Google Maps, right? And this is the Assiniboine spillway that we see just above it right here. And I think in the next slide, I'm zooming in on the spillway. Check this out. This is the Assiniboine River flowing in here. This is a huge spillway carved by glacial meltwater megafloods. If we zoom in really close, what we're seeing here is a beautiful example of an underfit river, as it's called by geologists, where the modern river is extremely small compared to the channel that it's in. And the modern river did not create the channel that it's flowing in. Now, in this case, we know that. I mean, because this channel was not, because if we go back 14,000 years ago, 15,000 years ago, all of this was under glacial ice. This channel was not here, you see. This channel was produced when the glacial ice receded far enough back to expose the land and then subjected to these huge meltwater flows that came down and cut these spillways literally probably in a matter of weeks or even days, right? The modern river, Assiniboine River, logically is going to follow the ancient megachannel, right? Once any river flowing up here, right, on the upland, once it crosses into the depth of this channel, well, it's now going to be confined to the channel, isn't it? So it's now going to flow in that channel. And so we're going to see many examples of this. In fact, most rivers in North America are underfit. Most of them are. And occupy these gigantic channels that were created by these meltwater floods. The high-temperature magnetic spherules that they found exhibit morphologies and chemical compositions like those found in sediment dated to the Younger Dryas onset at approximately 40 other sites across nearly a quarter of the Earth's surface. The evidence is comparable to distal ejecta from known impacts and inconsistent with non-impact terrestrial mechanisms. If the Lake Hind area was influenced by a high-energy ET event, such as the ablation or atmospheric burst of a fragmented comet or chondritic meteor, this may have produced a high-energy, think about this, a high-energy seismic pulse or a thermal pulse that briefly increased surface temperatures. Either phenomena may have led to release of meltwater into regional drainage systems through destabilization of the Laurentide ice sheet margin, including failure of glacial dams upstream from Lake Hind that were holding back proglacial lakes. In addition, a large-scale ET event would have greatly increased the outflow of fresh water from the Laurentide ice sheet into the Arctic and North Atlantic oceans, as well as releasing large fluxes of icebergs into nearby oceans. This, in turn, would have disrupted the Atlantic Ocean's meridional overturning circulation that triggered Northern Hemisphere cooling. Glacial Lake Agassiz was the largest of these ice marginal lakes that abruptly overflowed at the onset of the Younger Dryas, coincidentally at the same time as the ET event and the drawdown of waters in Glacial Lake Hind, which lies just upstream from it.
So they're saying a seismic pulse could have created the heat?
No, they're saying that there might be two variants of the effects. One, a seismic pulse, right? Think of Tunguska exploding in the atmosphere, and all the talk we did about there was being possibly a seismic response, a 5-point-something earthquake was actually measured in response to that. Now, what would happen if you upsize Tunguska 10 or 100 times, or you multiplied the Tunguska by 10 or 100? Yeah, so a seismic pulse. See, a seismic pulse was induced in the Earth's crust in the area of the Tunguska explosion without that thing even striking the Earth. So
yeah, I would see that as fracturing the glacier.
Yeah.
Or the ice,
And then you've got the thermal pulse.
Yeah.
So let's think this. Let's think this process through in our heads. Seismic pulse, what you just said, fractures. Now, of course, if there's a direct impact into the ice sheet itself, well, obviously, that's going to create a seismic event throughout the ice, isn't it?
Yeah.
Right? I mean, the seismic, this wave, think what Brad felt when this 5.1 earthquake came through North Carolina. Imagine it's a 10.0 earthquake, right? But it's passing through the ice. What's it doing to that ice? Right? Now you got the thermal pulse. So add the thermal pulse into the seismic pulse. What you said, the seismic pulse is going to fracture the ice, right? Now you add in the thermal pulse, you're going to melt a lot of ice. So what's that water going to do? Well, is it not going to access the base of the ice sheet now quite readily because the ice is fractured? Let's assuming it is fractured all the way to the base, which certainly could be possible and would be. Well, I mean, look.
Yeah, and if you're having other seismic events in the actual crust, that's going to be breaking up ice underneath. It can be shattering the ice underneath, even if some of the above layers were not broken up.
Well, and then you're also going to have, I would imagine now, typically in an impact, you've got this material that's thrown up and it falls back to Earth, right? Let's say you've got an object that's 1,000 feet to 2,000 feet in diameter, Tunguska 150 feet. Now we're talking about an object. I say that besides because now we're talking about an object that's big enough to actually penetrate the atmosphere and strike whatever's beneath it, be that land, be that ocean, be that an ice sheet, right? It strikes the ice sheet or it blows up in the vicinity of the ice sheet. Either case, you have a large-scale fracturing. You have a large-scale thermal event that melts a lot of water. Now, if you've got an impact into the ice sheet itself, the question is that impact going to have enough energy to excavate the ice and some of the substrate and actually gouge out a crater? Now, a crater formed purely in ice is going to be just a temporary transient thing. It's not going to last long, is it? Like a crater into the earth. So you've got the transient crater in the ice. Now, just like when you have an impact into the ocean, the water surges out, but then it surges back in. The geologists and oceanographers, marine geologists that have been looking at that, called that the resurge wave.
Resurge wave.
Right? Yeah. Likely you would have a resurge wave into the ice, and you're going to have a tremendous amount of water ejected, forced under the ice sheet, right? Away from the epicenter, right? And then if there's actually a basin excavated into the ground, the water's going to rush back in under pressure back into that basin. And when it does that, just like what has been observed around submarine impacts, is that there's obvious desecration of the rim, which was caused by the inrushing waters coming back in, obscuring and eliminating large portions of the upraised rim. So that's one of the consequences of the resurge wave coming back in, is it tends to erode away the raised rim that would be there in a purely terrestrial crater. You would have similar thing with impact into an ice sheet, because the resurge wave is going to come back in. It's going to be loaded with sediment, and it's going to infill the basin with sediment, and it's going to obscure the rim. So if you're thinking about looking for evidence of an impact, and see, one of the constant refrains you hear from the critics is, well, you don't have an impact crater, you don't have an impact crater, you don't have an impact crater. Well, what if we're talking about, and this is what we're talking about, is impacts into the ice sheet? Well, now, clearly, you've got to be looking for a different suite of geomorphic features. You can't be thinking, oh, we're going to go out and find something that looks like Meteor Crater, Arizona, and it's going to date to the Younger Dryas boundary. No, that's not what we're going to find. So the key, I think, is mapping the meltwater events. And there were multiple meltwater events. That's where it gets really kind of sticky and interesting. All right. So in this Google Maps, if you look at this little area right here that's a little bit darker, see where Oak Lake is? My cursor's right there at Oak Lake. And then this shaded area represents the basin of Lake Hind. Now, what I'm going to call your attention to is a couple of things. These are spillways. You see these darker areas? You think, okay, those are rivers. Well, they're rivers, yeah, but what you're seeing here is actually oversized valleys that the rivers are flowing, and you're not really seeing the rivers at this scale. But notice here from Lake Hind, you've got a spillway flowing out this way to the southeast, and you got another one flowing out this way to the southwest. You've got this interesting Turtle Mountain upland right here. You got another one, kind of almost a partner to it, right up here as well. And notice over here, you've got a couple of these dark valley-like things here. So coming across, we've got one here, we've got one here, we've got one here. We got this one we can trace right back up to seeing it emanating from this darker area, which was the basin of Lake Hind. Now, up here above, notice that we have this darker channelized areas. We got a couple of them converging together here, coming together. And here I've superimposed an approximate map of Lake Hind. So you can see what we got here is a channel where water is flowing in, and here we've got water flowing out. And right over here was the Laurentide ice sheet. Now, what I'm going to do is we're going to look in this area. Let's back up one. We're going to look in this area right up in here where the Assiniboine River loops down. We saw that map earlier, and we're going to see some of the features that are on the floor of that. Now, the distance across here, each of these squares is 1 mile square, so you can figure that the distance across here is probably close to, well, let's see. Yeah, it's probably 10 miles across this whole complex here. You can see where the squares are the agricultural fields, and then you can see that they commence back here. You see the geometric regularity. But then in this zone between here, you see there's no agriculture being practiced because this is a massive erosional feature here. And notice the branching, how these flows parted and then flowed back together. Notice that there's a major channel down the middle of the complex here, and it has a river winding in it. That's the Assiniboine River.
What's the flow direction?
In this case, the flow direction is from left to right.
Left to right. Okay, that's what I was thinking because of the smaller channels. Yeah.
And we're going to be seeing a lot of these kinds of shapes right here. These kind of streamlined forms. Look at where my cursor is right here. See this kind of almost streamlined forms?
Yeah, in the middle of the erosional parts. Yeah.
Yeah. Okay, let's look at a Google map. And here you can see, again, the underfit. Notice that you have a bank right here. You've got another bank right here. That's the channel width. And then here's the river flowing in it. This is the Souris Spillway, just north of the U.S.-Canadian border. It says down here at the bottom, note large-scale SERs, streamlined erosional residuals. Here's one right here, bounded by this single contour line. Right here, you can see it. That is a streamlined form. It is, you see, when water flows and it erodes, it's trying to minimize the amount of hydrologic or hydraulic drag. And it does this by creating these fluvial forms, these aerodynamically shaped forms, just as in ship or boat design, the idea is to minimize the frictional drag, the hydraulic frictional drag of the object moving through the water. Well, it doesn't matter whether the object is moving through the water or the water is moving past the object. The tendency is to erode whatever it's eroding into a form that offers the least resistance, right? Well, it turns out that there's a very consistent type of a shape. And you'll notice there's actually two streamlined forms here, a larger one bounded by this contour line. Do you see me going around it with my cursor?
Yep.
and then a smaller one next to it. So for a short while, you can see here there was a channel flow through here. Main one came down here, and even the main one, the even more main one came down here and deepened this the most because that's the one the river now occupies. But you could almost think that for a temporary period of time during this flood, these things would have been like islands. Initially, at the initial peak discharge, they were probably submerged. In fact, I think it's almost certain they were submerged. But as water levels declined, they would have then emerged from the floods as islands. And then eventually, once the ice was gone, the floods ended. And so now you had a whole new ecological regime moving in to colonize this recently vacated landscape. Here is a Souris spillway view to the north. This is wow. Very similar to what we were just looking at. You see here the streamlined form.
I see it.
Almost in the shape of a boat or a canoe hull, right? And then here's the Souris River. And you can actually see over here, this where you've got the plowed fields and stuff, that's the edge of the spillway over here. And then on this side, you see the same thing. So you can see the whole spillway is several miles across, whereas here's the river flowing in it. This river did not create the spillway. It's just using the opportunity to occupy the spillway.
Right.
It did not create the spillway. Okay, so now let's go back up to Lake Hind and look at something that I think is quite interesting. I mean, Lake Oak Lake, which is now the last remnant of Lake Hind. And what do we immediately notice?
There's a nice arcuate form there on the right side of
Oak Lake. Noticed that too?
Yeah.
Aha.
Yeah.
All right. Well, there's more to get into on Lake Hind and what's going on there. So we'll pick that up next episode.
All right.
So we will stop share. Oh my gosh. You guys weren't kidding.
No, I'm serious.
You were serious.
I was definitely not joking.
We lost Kronos.